If I plug in 0, the square root of 0 is 0, the square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. So then I have the point 0, 0, 1, 1, 4, 2. I didn't draw my graph big enough. We'd go out to 9, up to 3, which shows me that my graph looks like this. Notice that I've labeled some points. Whenever you graph, this is what I want it to look like. This is what I'm looking for. You have to have your arrows. You have to have labeled your graph. And if we look here, our range is all of our possible y values, which I know I start at 0 and go up. This looks like it levels off, but it continues on forever into infinity. Okay. Now, let's do a similar example. Same directions, find the domain and range and graph. Y equals the square root of x plus 4. Okay, so for our domain, I'm going to take x plus 4 and I'm going to set it greater than or equal to 0. When I solve this for x, I get x is greater than or equal to negative 4. Okay, so x in the reals such that x is greater than or equal to negative 4, and I label it domain. Now here's a hint. This will always be true. The range is going to be y is greater than or equal to 0. This is always true when you have a square root. Okay, now the only reason this will change is if we add things outside of our square root, but for now we're not there, so y in the reals such that y is greater than or equal to 0. Okay, now to graph it, we remember from way back in, I think you're talking about in Math 8.7, but Algebra 1, graph translations. If I have x plus 4 in here, that's telling me that I'm moving my graph to the left 4. Okay, so 1, 2, 3, 4. I know my graph's going to look like this. Okay, now if you forget that, that's totally okay. Plug in values for x and y. Let's plug in the same. 0, 1, 4. If I plug in 0, if 0 plus 4, it gives me 2. So I know that I go through 0, 2. Okay, I'm going to make that a negative 4. Because if I plug in negative 4, I'm going to get 0. Negative 4 plus 4 is 0. Square root of 0 is 0. If I plug in 1, I get the square root of 5. So 1 up here, that's about the square root of 5. And we label our graph. You don't have to label every single point, but I want a few labeled. All right, let's do some more examples. I know that this is brand new material. Example 8, find domain and range of f of x is the square root of x over x minus 2. Okay, now I have two things I have to be concerned about. I not only have a radical, I have a denominator. So for my domain, I'm first going to say x minus 2 equals 0, which shows me that x cannot equal 2. Okay, but then I also know, since I have the radical x, that x is greater than or equal to 0. Okay, so when I write my domain, it always starts x in the reals such that x is greater than or equal to 0 and x cannot equal 2. Okay, you have to write that little caveat. Now, here's the fun thing about range. Y in the reals such that, okay, range is a lot better, okay, because there's nothing I can't have for y here. Okay? Now, you don't have to graph this, but if you're curious, the graph looks like this, which tells me that y in the reals, y can be everything. So there's two ways you could write it. You could say negative infinity is less than y is less than infinity, or you could say r in the reals such that y is an element of the reals, meaning that y could be anything. Okay? If you have questions on domain and range, please bring them to class. I know it's new. Let's talk about now classifying functions. Okay? A relation is something where every element of the domain corresponds to one or more elements of the range. What did this mean? It means that every function is a relation. Not every relation is a function, though. Okay, and I'm going to get into showing you how to identify these. Okay. Now, we also have this thing called 1-to-1. 1-to-1 means every element of the domain corresponds to no greater than one element of the range. If a function is 1-to-1, that means that we can find a inverse of it. Okay, now let me show you with these pictures here. So let's say this is my domain, and I give these values here, and this is my range, and I have just one value. Both of these go here. This is not a relation, okay, because these go to, well, hold on. Let's talk about functions. They're better. This is a function, which does mean it's a relation, okay, because each of our domain values only go to one range, okay? Now, what if we had something like this? Okay, this is not a relation because this guy doesn't have anyone that he's going to. Okay, now a 1-to-1 function looks like this. Each of these have something that they are going to. Okay, so let's do an example. Determine if a function, okay, so this is part A. B looks like this. Okay, so we have a lot of different things going on here. Okay, let's look at this first one. Now, each of our inputs has one output, so yes, This is a function. If we look here, this input has one output. This input has two outputs. Not a function. Okay, in C, this has an output, this has an output, this has no output. Not a function. But if we look at D, we have x in the reals, meaning we have all of the different real values. And we have this happening, y equals x plus 2, and it's giving us x plus 2, which tells me that this is my output, which means this is a function. Each of my inputs has this output, x plus 2. Okay, so you will be given problems like this. Well, you'll have diagrams to determine if they are functions. You'll also get problems like this. Are these functions? Okay, we're going to have a set containing a bunch of coordinate pairs. We're going to write them all down, then we'll talk about them. Okay. Again, remember, function. We're looking to see, does every input have one output? Okay? So, these are my inputs. This is an input, this is an input, this is an input, this is an input. If we notice, they're all different. And they each have one output, which tells me that yes, this is a function. Okay? Let's look here. These are my inputs. If we notice, these two are the same, and they have different outputs. This is not a function. Let's look at this one. These are all our inputs. Now, these two are the same, but they have the same output, which is just the same point repeated twice, so this is a function. Okay? And here, if we look at our inputs, they're all different. This is a function. Okay? You will need to be able to recognize if these are functions from these diagrams or from ordered pairs. Now, there's another way to test to see if it's a function. We have what's called the vertical line test. The vertical line tells us that, let's say we have this function here, which is y equals x squared, or f of x is x squared. If I was to draw a vertical line anywhere on this graph, I would see that it only touches my function once. So this is a function. Now, what if I had something like this? If I draw a vertical line, it touches my graph twice. This is not a function. Okay, that's our vertical line test. Okay, a function means a vertical line only touches graph once. Okay, now we have this other thing, horizontal line test. Okay, this determines if a function is 1 to 1. Okay, so let's again look at the same graph here. If I draw a horizontal line, it touches my graph in two places. This is not 1 to 1. But what if I draw this, which is the line y equals x? Anywhere I draw a horizontal line, it only touches my graph once. Therefore, this is 1, 2, 1. Okay, so let's do a couple quick examples, or one quick example. I'm going to have these different graphs for you. And I want to determine which of these is a function. Now, if I look at A, if I draw a vertical line, it touches my graph in lots of places. This is not a function. Okay, if I look at B, my vertical line passes my vertical line test. This is a function. Now let's look at C. I have a closed dot here, so a vertical line, it passes there. But if I draw a vertical line right down the y-axis, it touches my graph twice, here and here. It's not a function. But let's look at D. Again, if I draw the same vertical line, because this is an open circle, that means the graph does not exist there. It only exists here, so that is a function. Okay? All right, that's our last example for today. Now, I know this is a lot and a longer video, okay? But please make sure that you go slow, and if you have any questions, write them down so we can talk about it after the long weekend. All right, have a good weekend.